Okay, this is Unit 12, Lesson 1. We're going to do kind of just an overview, an intro to these right triangles. So a lot of these things you have seen before in geometry, so we're going to kind of just push right through all this stuff on the front page. First little box here is just a reminder of the Pythagorean theorem. We all know this, and this is going to carry us through a lot of the stuff that we're doing for the rest of the lesson today. So if you have a right triangle, we know that the C is always the hypotenuse, and that is the one that is across from the right angles. That's what that arrow is showing us right here. So the formula is that a squared plus b squared is equal to c squared. So a and b are always the legs, does not matter which one is which, but then c is always the hypotenuse. So we're going to look at this question right here. The directions are to find the missing side. So we know 22, 24, and then this is x. So the right angle is right here, which means c is right here. So a squared plus b squared equals c squared becomes x squared plus 22 squared equals 24 squared. All right, so we set that up. It is very, very important that the hypotenuse goes in the correct spot. We've got some big numbers here, so I'm going to plug these into a calculator. So we have x squared plus 22 squared. So x squared plus 484 equals 24 squared, which is 576. So we can solve for x this way. So solving for x means we subtract the 484 from both sides, and so that gives us 92. And then we take the square root of both sides. So ordinarily, when you are taking a square root like this, we always start with a plus or minus. However, this is a side length, so we know it's going to be positive. So simplest radical form, the 92 can split into 4 and 23. So we know that 4 is a perfect square. So square root of 4 brings the 2 out, and then the 23 stays behind. That's prime. So that's as simplified as that is going to go, which makes sure we're following the directions here. Simplest radical form. All right, so that's the Pythagorean theorem. That will carry us into special right triangles. So I'm going to fill in these dimensions right here. This comes from geometry. You guys should have done those special right triangles, the 30, 60, 90, and the 45, 45, 90. So remember with 45, 45, 90, if these two angles are the same, that means that these two legs are the same length. Okay, so we call each leg x, so x and x. And then if we were to use the Pythagorean theorem, if we were to plug in x for a, x for b, and then solve for c, what we end up here is getting the hypotenuse is the short leg, or the same leg, I guess, times the square root of 2. So that formula will work itself out every time. So this is one of those things we just need to memorize. This tells us the relationship between these three legs of a right triangle. Then the 30, 60, 90, if we know that one of these is 60, we know the other one is 30. We call the short leg x. So I should label these. This is x, which means this is also x. We call the short leg x. The hypotenuse is always twice the short leg if you're in a 30, 60, 90. So that's 2 times x. And then if we do the Pythagorean theorem, we figure out that the longer of the two legs, not the longest side, but the longer of the two legs, ends up being the short side times the square root of 3. So x times the square root of 3. All right, so these, again, should be familiar from geometry, just one of those things that we are supposed to memorize for those two different types of special triangles. So let's do these examples down our right-hand column here, looking at these evens. So we are going to find the missing sides. They tell you what the angles are, which means we see this. If this is 45, this is 45, so this must be one of these triangles that we're working with right here. So x and y have to be the same length. We know that for sure. And we know that this is the hypotenuse, which is equal to this dimension right here. Okay, so we know that x equals y. That's one important thing to note here, is we know that this leg is equal to this leg because it's a 45, 45, 90. And we know that x is that dimension right there. So x root 2 comes out equal to 16. So we can say that x root 2 is equal to 16, and then we solve for x by dividing both sides by the square root of 2. All right, so divide both sides by the square root of 2, and then we are not supposed to have irrational values in the denominator, so we can rationalize. Remember, the way we do that is we multiply top and bottom by the square root of 2. So we have 16 root 2. The denominator ends up being the square root of 4, which is 2, and then that reduces down. So the 16 over 2 reduces down to 8 times the square root of 2. And then y is the very same dimension. The two legs are the same. So if x is 8 root 2, then y is also 8 root 2. Okay, let's look at number 6. We see the 30, which means that this is 60, and we can find the dimensions that we're working with here. So the hypotenuse is 8, so we just kind of compare up here. If the hypotenuse is 8, that dimension is 2x. Okay, so 2x is equal to 8. Divide both sides. That means that x is equal to 4. So that's our shorter side right here. So we know that x is equal to 4. And y is the medium length, which is the longer of the two legs. So it's just whatever x is times the square root of 3. So whatever x is times the square root of 3. Those are those two dimensions. All right, so now one more for the special triangles. We'll look at number 8. This is the hypotenuse. This is the longer of the two legs. This is the shorter of the two legs. All right, so this is across from the 30. So this is the shorter of the two legs. So this one, the hypotenuse, this one is always double that. So x is the hypotenuse, and that is double whatever the short side is. So we just multiply the 2 times 5, and we get 10 root 6, which does not reduce down at all. So the hypotenuse is double the short side. So instead of 5 root 6, it's 10 root 6. And then the medium side is the short side times the square root of 3. So the medium side is the short side times the square root of 3. So those would multiply together. The root 6 and the root 3 multiply together, and they give us root 18. And then the 18 can simplify down. So the 18 is 9 and 2. Square root of 9 is 3. Multiply that by the 5, and I get 15 times the square root of 2, which is what's left underneath there. All right, so that's some special triangle stuff. Let's look at our next page. Next page, we start looking at some trigonometric functions, and this is, again, should just be a review from what you guys did in geometry. So our trig functions, you guys hopefully remember SOHCAHTOA. A trig function is a function whose rule is defined by a trigonometric ratio. So a ratio would be one side length in the numerator, one side length in the denominator. So between A, B, and C, we could come up with 6 possible different ratios, and so each of those 6 possible different ratios has its own name. All right, so the ratio compares the lengths of 2 sides of the triangle. So maybe A over B, maybe C over B, maybe C over A. And then the Greek letter theta, so it's like a 0 and then with a horizontal line through it, and that is pronounced as theta, is used to represent the angle. So the acute angle, this guy right here. So in relation to this angle, you can talk about all of these different side lengths. So you guys hopefully remember SOHCAHTOA. Okay, so SOHCAHTOA I will write just as a reminder right here. I'm sure you guys did that in geometry. So SOHCAHTOA helps us remember that sine is the opposite side over the hypotenuse. Cosine, so here's C for cosine, is the adjacent side over the hypotenuse. And tangent is the opposite side over the adjacent side. So just a quick reminder of those definitions. Now, if we relate it back to this picture over here, here's the theta. We're specifically talking about this angle. So the opposite side to that angle would be A over here. And then the hypotenuse is C. So this one would be A over C in relation to this specific triangle right here. Cosine is the adjacent side. So the adjacent side is the one that touches the angle but isn't the hypotenuse. So the adjacent side to this angle is B. The hypotenuse is C. So the hypotenuse doesn't change because it's always across from the right angle, but if you're looking at this angle, this side is opposite and this side is adjacent. But if for some reason you were talking about this angle, this side would be adjacent and this side would be opposite. So make sure you're paying very careful attention. All right, the opposite to this angle would be A over the adjacent to this angle, which would be B. Okay, so you see we've got 3 different side lengths, A over C, B over C, A over B, but I said there's a bunch of different combinations, like we could do C over A, we could do C over B, we could do B over A. We haven't talked about any of those yet. So there are 3 different other trig functions that maybe you're not as familiar with. I know we're very familiar with sine, cosine, and tangent. We have 3 new ones, which are cosecant, secant, and cotangent. And each of those are the reciprocals of these ones that we already know. So 1 over sine means that cosecant and sine are reciprocals of each other. That means if sine is opposite over hypotenuse, then cosecant would be hypotenuse over opposite. And this is just the 3-letter abbreviation that we use for it. So in this triangle, instead of A over C, it'd be C over A, the hypotenuse over the opposite. Our second new one, secant, is the reciprocal of cosine. So we take the cosine measurement and we flip it. So adjacent over hypotenuse becomes hypotenuse over adjacent, which means B over C becomes C over B when we're talking about that triangle. And our third new one, cotangent, is the reciprocal of tangent. So we flip this one. So opposite over adjacent becomes adjacent over opposite. And A over B becomes B over A. So those are our three new ones. We are going to look at some new examples here where we can talk about all 6 trig ratios for these new functions. All right, so we're going to look at number 10 here. Given the ratio for cosines, they give us one of the 6, and then we're going to use that to find the other 5. So whenever you have one of these, we can set up a little right triangle here. So if we make this our angle, or our right angle, make this our angle theta. Cosine, remember, cosine is the adjacent side over the hypotenuse. So 2 would be the adjacent side, 3 would be the hypotenuse. So the adjacent side to that angle, we can label it as 2. The hypotenuse for that triangle, we can label it as 3. So that just means we need the third one. And to find the third one, we need the Pythagorean theorem. All right, so to find our third angle, this one right here, we're going to say x squared plus 2 squared is equal to 3 squared. So plug those into the Pythagorean theorem, we can find our missing piece. So x squared plus 2 squared is 4, 3 squared is 9. Subtract the 4 from both sides, we get x squared equals 5. And then to solve for x, we take the square root of both sides. Normally we do a plus or minus, but since we're talking about geometry and side lengths, we know it's just going to be the positive one. So we can label our third side the square root of 5. So now we know all of these, we can set these up. So I would think SOHCAHTOA here. So sine is opposite, which is the square root of 5, over the adjacent, over the hypotenuse, which is 3. So sine is opposite over hypotenuse. Cosine we already have. Tangent is opposite over adjacent. So opposite is root 5 over adjacent, which is 2. So we've got those ones. And then the other 3 are just the reciprocals of these ones. So this one, flip, and we have 3 over root 5. We don't want to leave a root 5 in the denominator, so we multiply by root 5 over root 5. Remember, when you multiply root 5 by root 5, you just get 5. Secant is the reciprocal of cosine, so 2 over 3 becomes 3 over 2. Nothing to rationalize there. And cotangent is the reciprocal of tangent, so root 5 over 2 becomes 2 over root 5. And then we rationalize that one as well. Multiply the numerator by root 5, multiply the denominator by root 5, and we get rid of that radical. Okay, so one final section down here, special trig ratios of special angles. So we are looking at 45, 30, and 60, and this is something that we're going to work with in future sections. So just a reminder, I'm going to label some pieces on our special triangles. So remember 45, 45, 90, we called these ones x, and we said that the hypotenuse was the square root of 2 times x. In our 30, 60, 90, the shortest side, we called that x. The hypotenuse was double the shortest side, and then the medium leg was the square root of 3 times that short side. So just a reminder of those. We can fill in all of these things. So the 45-degree angle, if we use this as a reference, sine would be the opposite side over the hypotenuse, which is x times the square root of 2. So no matter what x is, it cancels. So the x's cancel. We have 1 over the square root of 2. And then if you multiply top and bottom, multiply the numerator by the square root of 2, multiply the denominator by the square root of 2. So this is the sine of 45 degrees. So that's something that we will start working with in the future. Cosine of 45 degrees. This is our 45-degree angle. Cosine would be the adjacent side over the hypotenuse. And the exact same thing ends up happening here. Okay, so this is the same value, this is the same value. So we know it's going to end up being root 2 over 2. So these 9 values we will eventually have memorized, but today I'm just introducing them to you. Tangent of 45 degrees. This is 45 degrees. Tangent is the opposite over the adjacent. Of course, x over x is just 1. So the tangent of 45 degrees is 1. Notice these end up being actual numerical values. They don't have these, x's in them anymore. All right, now let's look at 30 degrees. So look at 30 degrees as our reference right here. Sine is the opposite over the hypotenuse, which is 2x. So the x's cancel and I get 1/2. Cosine of 30 degrees is the adjacent over the hypotenuse. So the x's cancel here, and I get the square root of 3 over 2. And tangent of 30 degrees, so here's 30 degrees, would be the opposite over the adjacent. The x's cancel, so I have 1 over root 3, but just like we did over here, we don't leave that root 3, so we multiply the numerator by the square root of 3, multiply the denominator by the square root of 3. And one last angle here, 60, so now we're using 60 as our reference angle. This is the one we're looking at, so this is now adjacent to the 60 degrees, and this is now opposite of the 60 degrees. So sine would be opposite of 60 degrees over the hypotenuse. The x's cancel here, and I get root 3 over 2. Cosine of 60 degrees, so here's 60 degrees. Cosine is adjacent over the hypotenuse. X's cancel here, and I get 1/2. And tangent, here's the 60 degrees. Tangent would be the opposite over the adjacent, and the x's cancel here and leave you just with the square root of 3. So those 9, like I said, will eventually be memorized, but for now I'm just introducing you to where they came from.